All right. Whoa, that's. And you may have heard of some aromatic compounds, such as benzene. I think everybody knows what a benzene ring is at this point in this class, right? And it's an incredibly important part of chemistry, and you've probably noticed this. You've probably seen structures all the time that have these rings, and here are just a collection of really common drugs. Lipitor in the upper left is a cholesterol-lowering drug, one of the biggest selling drugs in the world, has been for many years, just went off patent, I think. You've got, and it's not just one type of drug. There's a neat picture in your book. You've got everything from proton pump inhibitors, for acid reflux disease, to mood-altering drugs, to, what else is up here? Asthma drugs, all kinds of stuff. All having these parts. And as you've seen in this class, this benzene ring keeps coming up over and over and over again. So there must be something special about it. And this chapter attempts to answer that question. And we're going to say, what is special about benzene? And the thing that's special about benzene is it's what we call an aromatic compound. So we're going to go through what this means, but first let's just put this up there. This is benzene, as you know. Okay. And there's something special about benzene. Right? There's a reason that it comes up in natural products all over the place. There's a reason that many different fields of study, many different parts of study need benzene and use benzene. So first, let's talk a little bit about some nomenclature of benzene, how we talk about it, and then we'll get into the theory behind what's actually going on and why benzene is so stable. So some of these you know, some of these you don't, but you should know all of them after today, all right? So these are the substituted benzenes. And these are common names, but after today, these will be the accepted names. Okay. So it's generally considered incorrect to name these in a different way than these common names. I'll draw we'll just do it generally. We'll say an R here. So these are all substituted benzenes, meaning benzene with one thing coming off in one spot. And we'll set up a little table here. Now when R is a methyl group, what's the name of that molecule? Anybody know? We got that one. That's toluene. What about when the R is an alcohol? Yeah, phenol. Or sometimes pronounced phenol. It's fine. All right. What if we have an acid group over there? You know that one? Benzoic acid, right? All right. This one, I'd be surprised. Anybody knew this one? Anybody know that one? If it's a methoxy group on benzene, make that. What? Not quite. This is. We will talk about that one also. This is anisole. What?
There's like 14 of these in the book, isn't there? There's quite a few of them.
There's a lot of them, yeah. There's a lot of different ones. These are, I'd say, the most basic ones that are important that you know. What if it's an aldehyde? That one now is benzaldehyde. And then, you know this one? You mean? That's aniline. And then the methyl ketone is acetophenone. That actually isn't that strange of a name. The thing that makes it a common name is the old version of a 2-carbon chain. Now it's always has a prefix of eth or a root of eth something, ethane, ethanol. Used to be ACET, like acetic acid, acetaldehyde, acetophenone. So that's where that comes from. And then last one, if you have a vinyl group coming off there, that's known as styrene. And styrene is most common in polystyrene, which is the polymer that we make styrofoam from. We'll probably talk about that. We'll get into polymers a little bit later in the semester, if we have time for that. Okay, naming benzene-related things. Well, first of all, if the benzene is smaller than the rest of the molecule, we treat it as a substituent. And benzene as a substituent is called what? Okay, you got to be careful here. This is a common mistake, and it is totally confusing, so I understand. It's phenyl. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 3-phenyldecane. Now this is not actually called this, but so I'm not gonna write the name because it's not correct. But this is a benzyl group. Phenyl refers to the ring itself. Benzyl refers to ring with a methyl group, so the carbon. We talk about a benzyl radical or a benzyl cation. Benzyl alcohol is that molecule with an OH. So remember that as a substituent, phenyl. Okay. Now when benzene is the main part of the molecule, we name it as a benzene. So things like this are known as (2-bromotoluene). So the number 1, normally our priority goes with atomic number and other stuff. But in benzene, if you're using one of those names that we just talked about, carbon number 1 is always the carbon that thing comes off of. So if it's toluene, then carbon number 1 must be the methyl group. If it's phenol, then carbon number 1 must be the alcohol, or the carbon with the alcohol. And there's another way we can name these also. Does anybody know? Well, we can't do that because we call it a toluene, but still calling it a toluene, we can talk about the relationship that these have to each other. And that relationship comes about because there are only 3 possible relationships that a di-substituted benzene can have, that the substituents on a di-substituted benzene can have. Let's draw them. Because benzene is flat and symmetrical, the 1, 2, 1, 3, and 1, 4 are the only possible disubstituted benzenes. Because 1, 5 is the same as 1, 3, and 1, 6 is the same as 1, 2. So they're given special names. This one is known as ortho, the 1, 2. The 1, 3 is known as meta, and the 1, 4 is known as para. And the important thing to keep in mind here, because I always see this mistake, is that this is only for benzene. It doesn't work for cyclohexane because cyclohexane doesn't have the same symmetry. It doesn't work for larger molecules, naphthalenes or other types of things like that. We only use this terminology for benzene itself. So 2-bromotoluene can also be known as ortho-bromotoluene, or sometimes it's simply abbreviated with an O, O-bromotoluene. Let's try some other ones. So then what would you call this one? Well, what's the special name we're going to use here? Anisole. So it's an anisole, and then how do we finish the name? Right, 3-nitro or meta-nitro. Anisole. Okay, and we could have also said that was M, and we could also say 3. The numbering is also acceptable. And then an example of the other. What did you call that one? Right, parachlorobenzaldehyde. Or p-chlorobenzaldehyde or 4-chlorobenzaldehyde. Okay, and then I guess I kind of lied before. There's one more special name that you should know. Actually, there's a couple that'll come up over the chapter, but this one, does anybody know what that's called? How would you name it based on what we've just talked about? Yeah, either orthodimethylbenzene or orthomethyltoluene or 1,2-dimethylbenzene. In fact, this is known as orthoxylene. Xylene. It's a fairly common organic solvent. You can buy it at the hardware store. And then this one is meta-xylene. And paraxylene. The interesting thing about the xylenes is that they have different boiling points based on the geometry. The paraxylene is the highest boiling and the orthoxylene is the lowest boiling. So you can buy these as individual solvents, pure solvents of ortho, meta, or para, or you can get the solvent just known as xylenes, which is an unspecified mixture of these three. That's the most common that we see. It's a higher boiling solvent than toluene, so it's a little bit better if you need to get to higher temperatures or if you don't want it to be quite as volatile, but still does a nice job at dissolving stuff. It's fairly cheap too.
Which one has a higher boiling point?
The para. Why do you think that is?
Yeah, they fit better into not like the lattice.
Was dipole?
Yeah, that's actually true. Now, you have to be a little bit careful. When you talk about stacking or fitting, that usually applies more to melting point because things have to pack into a crystal structure as a solid, not as a liquid. But in this case, it's also true because the predominant intermolecular forces in benzene are actually the pi electrons, the double bonds kind of stacking and interacting with each other. Oh, and while we're talking about it, fine, one more you have to know. We'll probably come up with some other ones too, but for now, anybody know what that one is? That's naphthalene. This one's can be tricky to spell. Naphthalene is important for a lot of reasons, but most of us experience it in the form of mothballs, although probably not so much anymore. But if you've ever been up to an older relative's attic or trailer or something, and it has that particular smell, that's probably naphthalene. It's mothballs. Do they even sell those anymore? I don't know.
Yeah,
People still use them? Okay. Okay. So what happens then if it's polysubstituted? If we have multiple substituents? Let's say something like this. Can we call that meta-bromo-ortho-chlorophenol? Doesn't really work like that, unfortunately. All right, so let's remember this. There are no ortho, meta, and para if you have more than two substituents. And the reason for that is it becomes confusing. Okay, we get the first one, ortho-bromophenol, that's clear. But if it's meta-bromo, if it's meta-bromo-ortho-chloro, then is the bromo ortho to the chloro or to the phenol, or what's going on there? If you have if you have more than two substituents, you have more than one ortho-meta-para relationship. Because like the OH and the Cl are ortho to each other, but the Cl and Br are para to each other and all this stuff. So it just gets too confusing to name it that way. We go back to the old-fashioned numbering in that case. And this would be then 2 chloro, 5 bromo. Why doesn't the bromo come first in this case?
What's the substituents of the phenol on it? The alcohol's going to
Is
be.
it the closest group to the OH?
No, you want yes, in a way. You want the lowest possible numbers for the last substituent.
No, but that's
So if you named it the other way, it would be a 3 bromo 6 chloro.
No, but my point is like, we put 5 bromo because of the alphabetical order when we are naming.
Oh, yes, that's correct. I'm sorry. Yes. I thought you meant you'd give that the priority. Yes, you're right. This should be,
Always start with one on the parent.
yes. So this would be 5 bromo 2 chlorophenol. All right, how about this one? Yeah, you can blow some stuff up with that one. What would you name it?
Traditionally TNT.
One three or 235 nitro, trinitro, toluene.
Close. Check your numbers again.
235.
236.
246.
246. 246. If you get hung up on that, just write the numbers down. 1, 2, 3, 4. Whoops, I missed one. So I guess that doesn't help. 4. But if you know you don't make it to 6, something's wrong, because I hope you realize that there's 6 carbons there. So yes, that would be 2, 4, 6. Try nitrotoluene, otherwise known as TNT, dynamite. So I think this naming is relatively straightforward. As usual, there are some practice problems in your book. Now let's talk about the structure and the special stability of benzene. As you may have noticed, we've sort of been indiscriminately writing benzene in one of two ways as part of two resonance structures. Right, we draw it like this. And we draw it like this. What do you tell me? What do you think?
I don't think so. Aren't all those bonds like supposed to be calcium? That's why some people just draw a circle in them.
That's right. Careful, they're not moving, but they're actually an average of these two. So when you look at the structure of benzene, you don't actually see if either of those were the correct structure of benzene, then you should see 3 short bonds for the double bonds and 3 long bonds for the single bonds. And that was the first proposed structure. So you'd have something like this, right? Because double bonds are shorter than single bonds. And the original proposed structure by Kekule, he said that that's probably what happened, but then they flipped back and forth. And they actually were switching like an equilibrium process. But then later, it was found that, in fact, it's not an equilibrium process. It actually is an average of those two all the time. And so a lot of people will draw benzene with a circle in the middle to show that, in fact, it's an average of all of them. Now, especially when you get into biochemistry, or when you look in older textbooks, older diagrams, this often comes up. And there's nothing wrong with that per se. Everybody knows if you see that, you're talking about benzene. The reason that we use these diagrams is because we draw mechanisms, right? We draw the little arrows, and it's got 2 electrons going and doing this. And the point of those mechanisms is to keep track of electrons. It's a bookkeeping type thing. If you have something like this, it's a little bit harder to actually keep track of all those electrons. Where do these electrons go? Where does the cation form? That sort of thing. So benzene is sort of a generic part of a larger structure. This is fine. But benzene as something that reacts in a specific way, we tend to use this. So you'll find organic chemists mostly draw them this way. And then when you're just kind of expressing a larger structure like a drug or something, you might see this one instead. I guess that's all I have to say about that. When you're drawing mechanisms, make sure you're drawing this. If you're not drawing mechanisms, I don't care. All right. So here, let's talk a little bit then about the electronic structure of benzene. As you know, what do you get if you do this reaction? Right, you get the anti-addition of bromine plus the enantiomer. Okay. What happens if you do that with benzene? Or actually, no, let's not get there yet. What happens if you do that with cyclohexadiene? Yeah, which is really one of two because they're the same. So you get you can get this one, the 1,2 addition, oops, and the 1,4 addition. We talked about that in the last chapter. Okay. So now let's move to benzene. What happens if you just add one more double bond and react this with bromine? Nothing. Nothing. Why do you think that is? Yeah, because it's extremely stable. It's extremely stable. So let's look at another, let's look at a diagram here of some hydrogenation energies. So here are the energies of hydrogenation, which means how much energy is released when you hydrogenate these molecules to cyclohexane. So if you take a cyclohexene, should be about 120 kilojoules per mole. Cyclohexadiene, we would expect about 240. Why do we see 232 instead? Because of what? Yeah, but why isn't it exactly double this? Why is it a little bit less than double? Right, exactly. It's conjugated, and we talked in the last chapter about how that makes it a little bit more stable. So then if you keep the same pattern going, you would expect that 3 triple bonds with no relationship to each other would be 360 kilojoules per mole. That is triple this. Maybe minus a little bit for conjugation. But in fact, it's minus a ton. And that benzene is actually giving you out less energy than the diene, which has more hydrogen being added to it. So even though the resonance certainly has something to do with this, there must be something else even bigger, even more stabilizing than resonance that's causing this to happen. So let's talk about what that is. It actually comes from the molecular orbital theory. Aren't you excited that we're going back to that? So let's look at the molecular orbitals of benzene. We're not gonna totally derive them. I'll just show you the picture, because. All right. So here are 6. Remember, you got 6 free p orbitals, and when we looked at something like, whoa, did that just do something? Okay. Well, anyway, you've got 6 p orbitals, and remember when we talked about hexatriene, we said that those 6 would now form 6 molecular orbitals, going from 1, 2, 3, 4, 5, 6. And remember, we filled those things up, and I'm sure you've been working on that in your homework and all of that. Well, benzene is a little bit different because of the symmetry. So here are the molecular orbitals of benzene. Instead of them being all in a line now, of course, they're in a ring. And in the bottom, you have the one where they're all in phase, just like before. And the next 2 are actually equal in energy. There's one node. You can cut it one way or you can cut it another way, and you get one node either time. Then there's two ways that you can sort of double cut it and get two nodes in each one. That's here, so these two are degenerate, they're the same energy. And then you have the highest energy one where they're all alternating, just like in the hexatriene. All right? And since we have 6 electrons, we fill these bonding molecular orbitals, and we leave these anti-bonding molecular orbitals empty. And that perfect separation, where the bonding ones are all full and the anti-bonding ones are all empty, leads to this special stability. And we can actually define where we see this special special thing, and this is known as Cripples Rule. You can count up the pi electrons and if there is a number of pi electrons that can be expressed as 4n plus 2, where n is an integer, or a whole number, I guess. So 4n plus 2 pi electrons are especially stable. And let's think about what those numbers are. So if n equals 0, 4n plus 2 is what? 2. So a molecule that has this sort of ring with 2 electrons, and we'll talk about what that means exactly in a second, is going to be especially stable. What's the next equal number? 6, because when n equals 1, 4n plus 2 equals 6. So molecules with 6 pi electrons are going to be especially stable. What's the next one? 10. So you get the idea? And then 14. So these are the numbers of pi electrons that are especially stable. Now, there needs to be a couple other things that go your way to have this special stability. And in fact, this special stability is called aromaticity. So we say that something is aromatic if 1, it is a flat ring. Okay. So the butadienes, the hexatrienes, those are all conjugated, but they can't be aromatic. Aromatic is the special extra stability. So number 2, you need to have every atom in the ring has a p orbital, and they're all in conjugation with one another. So each ring atom, they don't have to be carbon, has a p orbital. And since it's flat, they have to all be in conjugation. So we don't really have to write that. If it's flat and they have p orbitals, all the p orbitals will line up and they'll all be in conjugation. And then the third part, which is what we just talked about, you need it to have 4n plus 2 pi electrons. So it's got to have either 2, 6, 10, 14, and so on pi electrons. So let's take a look at some of these. So first of all, let's just look at benzene. We know the answer already, but let's make sure it fits all our criteria. Is it a flat ring? Yeah. Does each ring atom have a p orbital? Yes, they're all sp2 hybridized. So we could probably say that here also, with a few exceptions where you could have sp hybridization. Generally, you're going to be looking for sp2 hybridization on all atoms. And then how many pi electrons does it have? 6. So we could say 1, yes, 2, yes, 3, 6 pi electrons, yes. So then it is aromatic. And what does that mean to us? Why is that important? Well, it means it's especially stable. So when you're looking at reactions and you're trying to think, well, will this happen? Will this happen? If you can make something aromatic, that's probably what's going to happen. Okay. Let's try another one. Cyclobutadiene. Is that a flat ring? Yeah. Oh, it is. It is a flat ring. It's strained, certainly. Does each ring atom have a p orbital?
Yes.
Yep, they're all sp2 hybridized. And does it have 4n plus 2 pi electrons? No. How many pi electrons does it have? 4. So it's not aromatic. All right, what about this one? Hold on, I didn't draw it right though. Yes, this is a heptane. And it's actually a cation heptane. A cationic heptane. So a heptane with a carbocation on it. In other words, a cycloheptatrienal cation. Is that a flat ring?
Yes.
It is. Does each ring atom have a p orbital, or is sp2 hybridized?
Yes.
It is. And the tricky part here is this cation. What's the hybridization of a carbocation generally? sp2. Right? It's got 3 things on it. It's flat sp2. So it does. And then how many pi electrons does it have? 6. So yes, this one is also aromatic. Now let's look at the non-cation version. Regular old cycloheptatriene. Is that one aromatic? How do you know? That's right, it has an sp3 hybridized carbon. So that's not flat. Well, it might be flat, but it certainly doesn't have a p orbital there. So it's not aromatic. So what does that tell you then about, well, let's look at one more part and then we'll talk about that question. Let's look at the cycloheptatrienal anion. Is the anion aromatic?
No.
Why not? Well, this is where it gets a little bit tricky.
7.
Not quite, but you have to go back on something that you were probably taught in an earlier class, which is unfortunately how science works a lot of the time. We're going to come back to that one. Let's try this one first. This is a molecule called furan. Now, is this one aromatic? It actually is. And here's why, and here's where you kind of have to go back on something. Lone pairs, we think of them as groups in terms of the hybridization, but in fact, they can occupy any kind of orbital. Okay. So a lone pair can be in a hybrid orbital, and this can be sp3 hybridized, or it can be in a p orbital, and this could be sp2 hybridized. So let's draw those and look at them. We'll kind of go from the side here. So if it's sp3 hybridized, then the two lone pairs are in sp3 hybrid orbitals that kind of stick out at an angle. But it can also be sp2 hybridized, where one of the electrons is in the sp3 hybrid orbital, or in the sp2 hybrid orbital, and the other pair of electrons is in a p orbital. Depending on the rest of the molecule, one may be more likely than the other. In this case, the sp2 is more likely because then it can be in conjugation with all the rest of these p orbitals. Making this thing aromatic, because now those two electrons actually count in the pi electrons because they're in the pi system. They're in a p orbital. So those two electrons count in the pi system. Therefore, this molecule has 2 electrons from this, 2 electrons from this, and 2 from that lone pair. That's 6 pi electrons. And that makes it aromatic. Now, if you had a molecule like tetrahydrofuran, without the double bonds, yeah.
So it both is and it isn't aromatic?
No, it is. It absolutely is.
But we would expect to see those in sp2.
Right. When the electrons can be in the sp2 orbital, or if the electrons can be in a p orbital, and that would make the molecule aromatic, then that's what happens, because that increases stability so much. But in a molecule like this, THF, there's no energetic reason for the electrons to occupy a p orbital versus an sp hybrid orbital, because they're not going to be in resonance with anything else. So in this case, that oxygen is going to be sp3 hybridized. Okay. Now back up to this question. Does putting those 2 electrons make this in the p orbital make this molecule aromatic? Up in the heptatrienol anion? If they're in the p orbital, it would not be aromatic because that would be 8 electrons, right?
So for stability's sake, is it not going to be instead of the sp3 hybridized?
That's right. So this one actually wouldn't hybridize that way. Wouldn't hybridize sp2. It would stay sp3 because there's no energetic favorability. You don't get that aromaticity, and in fact, you get the opposite, known as anti-aromaticity, which we'll get to now.
Before you go on,
Yeah.
I understand why you would get 8 pi electrons of that
Mhm.
here occupies it, but I don't exactly understand the hybridization.
Here,
Is that sp3 then?
probably. I'm not. That one could kind of go either way. There's no great energetic advantage for it to go sp2 because it wouldn't be aromatic. We're going to talk about this right now, and actually the best way to answer this question is going to be to look at the molecular orbitals. So let me show you something called Frost circles, which is a quick and easy way to derive the molecular orbitals of these ring compounds. And then we'll come back to that question and see what everybody thinks. If you notice, let me remind here. Sorry, okay. If you notice, the electrons, or the molecular orbitals for benzene look like this. And there's 6 of them, and if you look at them, they kind of look like a benzene ring, right? Like they look like the points of a benzene ring going around. that's actually not trivial. Somebody recognized that and found it as a nice, quick shortcut to actually figuring out these molecular orbitals. So if you have something like benzene, you can put it on a point, make sure it's sitting on its point, and then if you just draw lines where the carbons are, you actually come up with a molecular orbital diagram for benzene. It's called a Frost circle because he said you should actually inscribe this thing inside a circle with its point down. But the point of all of this is that you get this, which is indeed the molecular orbital diagram, if you put it on an energy axis, for benzene. Then you just have to fill it up with electrons. We know benzene has 6 electrons. Didn't quite build those up right, but you get the idea. So now we have a molecular orbital diagram for benzene. And in fact, we can do the same thing with any of these rings and get some ideas about what's special about these molecular orbitals. So let's take cyclobutadiene. You turn it on its end. Okay. And then this is what the orbitals look like, one at each point. So the molecular orbital diagram for cyclobutadiene looks like this. And how many electrons do we fill it with? 4. All right. And now you can see the very big difference in these two. Here you have a clear separation between bonding and anti-bonding orbitals, and the bonding ones are filled with electrons and the anti-bonding ones are empty. In cyclobutadiene, there isn't that. And in fact, these middle electrons are sort of on non-bonding territory and are not stabilizing the overall interaction. And that's actually why we see that as being less stable. And these reactive unpaired electrons actually make this thing what's called anti-aromatic. So when you see those in a molecular orbital diagram, that's actually less stable. So you can think of the same idea as driving your reactions forward. If something is going to form something anti-aromatic, that's probably not going to happen, or it's probably going to take a lot more energy to do so. Yeah?
And then as far as the antibonding and bonding, like up there it makes sense for you to split it in half.
Mm-hmm.
Which ones are your antibonding?
It actually still splits right in the middle. So those middle electrons are non-bonding. And then the bottom ones are bonding, the top ones are anti-bonding. So that's actually not a stabilizing or a significantly stabilizing interaction. And the shorthand for that is you can always tell when something's going to be anti-aromatic if it has 4 n pi electrons instead of 4 n plus 2. That is a number that's divisible by 4. So 4, 8, 12, 12, 16, 20. Those are especially unstable. All right, so see if you can do this now for cyclooctatetraene, which is an 8-membered ring with 4 double bonds. So put it on its end, and then draw the molecular orbitals and fill them with electrons. And see what you come up with. Go like this. If you're having trouble drawing the 8-membered ring on its edge, right, you can draw the orbitals like this. Okay, just realize that now your energy axis kind of looks like this. So you have, if we're gonna do that properly now, that would be 1 on the bottom, and then 2, and then 2, and then 2, and then 1 on the top. So draw however you need to draw it, turn your paper or whatever. But it's important you get this way because otherwise your electron filling doesn't work. How many electrons do we fill with? 8. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. So what do you think about this molecule? It's got to be anti-aromatic. And because anti-aromatic is actually less stable, something interesting happens. And I'm going to try to draw this. I'll just show you the picture. Cyclooctatetraene actually ends up not being flat. Because being flat would make it anti-aromatic. And anti-aromatic is actually less stable than just not aromatic. So it actually bends to prevent itself from being anti-aromatic.
But I thought it's aromatic if it's flat.
No, it's aromatic if it's flat and has the proper separation of electrons, 4n plus 2 electrons. The electrons filling only the bonding orbitals. If instead the electrons fill some of those, you have unpaired electrons in the non-bonding one, it's less stable and therefore that's anti-aromatic, which is sort of worse.
So this way, when it's bending, it's preventing itself from being anti-aromatic?
That's
but
right.
Still not aromatic.
That's right. So these double bonds in cyclooctatetraene are actually not in conjugation. They're individual, separate double bonds because of that. So now that we've kind of gone through some of the theory, let's talk about in practice how you use this to figure out what might go on in a molecule. Okay, so let's take cyclopentadiene. Is that aromatic as it's drawn there? It's not. So, what about these hydrogens? Let's say I asked you if you think those hydrogens would be particularly acidic. That's a question that aromaticity can help you answer. That is, do they have a low pKa? Can they be easily deprotonated? Now normally, you would say, well no, carbon-hydrogen, sp3 carbon-hydrogen bonds have super high pKa's, like 50, 60, something like that. But resonance actually changes that. So let's look at what happens when a base deprotonates cyclopentadiene. We look at the conjugate base, as always when we're judging acidity. So that's the conjugate base. Is that conjugate base aromatic? Let's go through the rules. Is it flat? Yeah, or it can be. Do we have a p orbital on each atom? Can they all be sp2 hybridized? They can. They don't have to be, but they can because of what we said, that a lone pair can occupy a p orbital or a hybrid orbital. So it can be sp2 hybridized. And then what about the electron count? How many pi electrons? 6. So that's aromatic, right? Yes, that would actually make it a pretty good acid. The pKa of this molecule is 16, which is about the same as water. So in this case, the drive toward aromaticity makes a CH bond about as acidic as water, the OH bond in water, which is a huge difference. Even some of the more acidic CH bonds that we've seen so far, the ones in triple bonds, are on the order of 25. So those are the kinds of questions that you can answer here. Let's go back to the one we saw before. Let's talk about this cycloheptatrienyl anion. based on this anion, would you expect cycloheptatriene to be acidic or not?
No, it's not aromatic.
What is it?
The 8 pi electrons.
That's right. So this is actually anti-aromatic. So you might expect this pKa to be exceptionally high. And it is. And in fact, just like cyclooctatetraene, if you do manage to get a strong enough base to deprotonate it, it actually doesn't stay flat and anti-aromatic. It twists itself up to be not aromatic. Okay, what other kinds of questions can we answer? We can look at things like this. Let's go back to that cycloheptatriene. But let's look at a cycloheptatrienyl bromide. Let's say we react this with sodium hydroxide to do a substitution reaction. Would you expect that to be SN1 or SN2?
Listen to
Why?
because you can't perform carbocation
Why not?
because you can't have a double bond on you can't have two double bonds at one time. Or no, that doesn't make sense.
That's true, but I'm not sure that applies to this molecule.
It's SM,
Yeah.
SM2 because it's not just going to fall off. It's not very stable.
Okay. What were you going to say?
One is a living group and then it's a good living group, so electron.
Okay. Well, those are all nice and generally correct responses. Yeah.
If you had a carbocation with one of the pi orbitals, just put over the vacant orbital that would be on the carbocation.
Mm-hmm. What do you mean? Would it fill?
Well, I mean, because it carbocation is positive, so would it be a pi electron move over to the vacant p orbital on the carbocation? You know what I'm saying?
The electrons can't quite move like that, but it could be in conjugation in resonance. Shilpi, yeah.
Well, I was gonna say that possibly the carbocation, if it does form a carbocation, that carbocation would be aromatic like we talked about, so it wouldn't want the OH group to come in.
Okay. Yeah. You're on a right track.
No, it should be 8 pi electrons.
Well, let's go ahead and look at it. In fact,
And that's energetic.
this reaction does go by SN1, and it's fast. It's a very fast SN1 reaction. And let's look at why. Again, nobody said anything wrong. Your arguments were all good. But there's a special situation here. That's the intermediate for the reaction. And this molecule is aromatic. That molecule, right? We went through that before. It has 6 pi electrons. The carbocation is also sp2 hybridized, so there's a empty p orbital there. And we know that the first step of an SN1 reaction is the rate determining step. So the faster you can form a carbocation, the faster that reaction will go. And in fact, this reaction is extremely fast. So fast, in fact, that this molecule, cycloheptatrienyl bromide, is actually soluble in water, even though it's not really polar at all. But as soon as you get it in water, it dissociates into the carbocation, and the carbocation is exceptionally stable because it's aromatic. All right, last question, and then we're done for today. Which of these two molecules is a stronger base? That molecule is known as pyrrole. And this one's pyridine. Pyrrole or pyridine. And why? So think about that. Check some aromaticity. Oh, this one has one lone pair too. And let me know what you think. All right, what do you think? Who says pyrrole is the stronger base? Okay, who says pyridine is the stronger base? Couple more. All right, we gotta try again. Everybody's got to vote. You gotta have an opinion. Who says pyrrole is the stronger base? Okay, who says pyridine is the stronger base? Still see no opinions, but all right. I guess that's it. Okay. Well, first of all, before I ask you for your reasons, which of these are aromatic? Okay, pyrrole is aromatic. Is pyridine aromatic? Actually, it is. How many pi electrons are in pyridine? 6. 6. Why is this electron, why am I not counting that? Yeah, let's look at the geometry of pyridine. Kind of look at it on its side. Okay, there's no hydrogen there, right? So you've got your p orbitals all around the ring. Okay. That double bond is already there, right? So that it's sp2 hybridized, which means that lone pair must be coming out here in the sp2 orbital. There's no more room in there to do it. You can't have two p orbitals occupying the same space. Okay, so they are both aromatic. Does that change your answer?
Wait, what is that hybridization mean?
sp2.
No, just give my gut.
It's sp2, but the lone pair is not in the p orbital. It's in the sp2 hybrid orbital. It's not part of the pi system. All right, well, that doesn't change your answer. Let's look at the conjugate acids. We protonate both of these. Whoops. Here is protonated pyrrole, right? And here is protonated pyridine. So looking at those two conjugate acids, is one of them clearly more stable than the other? Let's look at the aromaticity again. We said that this was aromatic, right? And we said that this one was aromatic. Now let's look at those conjugate acids. Is this aromatic? It is. What about this one? It's not aromatic anymore because that nitrogen now no longer has the lone pair to be sp2 hybridized, so it has to be sp3 hybridized because it's got two hydrogens. So this is not aromatic. Then which must be the stronger base? The pyridine must be stronger. Because if you protonate pyrrole, it goes from being an aromatic base to a not aromatic acid. So that's not likely to happen. Another way you can express this is to say that these electrons are kind of tied up in the aromatic pi system, and they're not likely to go grab a hydrogen. Whereas these are outside of the pi system, and therefore more reactive. So if you've noticed these last couple acid-base questions I asked you, if it's not clear just looking at the molecules which one's a stronger base or a stronger acid, which is often the case, look at the conjugates. because that'll usually be your clue. In this case, it wasn't clear looking at these. They're both stable. They're both aromatic. But then when we looked at the acids, we saw that one was aromatic and one wasn't. And then same thing up here when I asked you about this one. It's not clear about the acidity of that until you look at this conjugate base and see that the conjugate base is aromatic. So start thinking about these things. When you see these ring systems, and I'm asking you questions about reactivities or stabilities or acid-base properties of ring systems, always be looking for that aromaticity because it's a big factor. Yeah?
Is this going to be on the quiz on Wednesday?
No.
Just chapter 17
Right. And everything else.
and everything else before
As usual.
that?
Right.